Okay, welcome everyone to our second lecture on Fourier methods in combinatorial number theory. So just so you're aware, this is being recorded, but hopefully that won't inhibit you into asking a question. If you do have a question, feel free to unmute yourself or raise your hand or put a question in the chat. I might miss some of the questions in the chat if I'm occupied trying to think about mathematics. If you've got any accessibility issues, for instance, with the video or the notes or the slides, do let me know and we'll try and resolve that together. So you can email me. The notes for the course are available on the webpage. And just to emphasize that these videos are about sort of a big picture. We're being a bit fast and loose with the rigor. And I've sort of put the rigor into the notes and not the slides. I hope that's okay with everyone. Okay. So let me make a start. So today we're going to talk about density increment. So let me give you an outline of how today's lecture is going to go. So I want to motivate this technique of density increment by talking about one of the sort of cornerstones of combinatorial number theory, which is Roth's theorem on three-term progressions. Dense sets of integers always contain three-term progressions. So we're going to prove that today, and we're going to prove it in a completely qualitative, non-quantitative way, basically because I just want to use it as a way to demonstrate this method of density increment. So we'll deduce Roth's theorem from a concept I like to call local Fourier uniformity. So any dense set of integers has a small piece which is Fourier uniform on a subprogression. And we can exhibit a three-term progression in our set by localizing to this little Fourier uniform piece. So Fourier uniformity implies Roth. So we reduce the task of proving Roth's theorem to establishing local Fourier uniformity, and we'll do that via this technique of density increment. So that's the outline for today. Okay. So let me motivate Roth's theorem by discussing this question of Erdős and Turan from the 30s. So this is perhaps asking to explain a result of van der Waerden, which says however you finitely partition the positive integers, at least one part of that partition contains infinitely many three-term progressions, and four-term progressions, and five-term progressions. Perhaps you can explain why van der Waerden's theorem is true in a different manner, and this is provoking this question of Erdős and Turan. How many numbers do you need to remove from an interval 1 up to capital N in order to remove all three-term progressions? So you look at this interval of 1 up to 8, and immediately you see at least one three-term progression, 1, 2, 3. So you have to delete in an element of this three-term progression. Let's delete the number 3. How many more three-term progressions have we got? Well, we've got 1, 4, 7. We need to delete an element from that three-term progression. And we've got 2, 4, 6. We need to delete an element from that. So let's do that. Have we managed to remove all three-term progressions? Well, if you stare at this long enough, you'll see you can jump 2 from 2, jump another 2. That's a common difference of 3, and you've got a three-term progression again. So we need to remove one of those elements. So let's delete 8. And a little case checking, you now deduce that you've deleted all three-term progressions. So the answer to Erdős and Turan's question for this particular interval, on the way we've done it, is we needed to remove, or I needed to remove 50% of the interval to destroy all three-term progressions. But that's not representative of the general case. So as the interval gets very, very long, you're not going to get away with only deleting 50% of the interval. You're going to have to delete all of the interval, or a proportion of the interval which approaches 100% as the interval gets longer. So you need to remove at least 100%. Another way of saying that more formally is, what's the largest subset of this interval you can come up with which doesn't have a three-term progression? And Roth's theorem says that largest subset has to be sparse. its order of magnitude of its size has to be an order of magnitude smaller than the length of the whole interval. So the proportion occupied decays as the length of the interval tends to infinity. And another way of phrasing that is, if you have a positive proportion of the interval, then you have to contain a 3-term progression. So here we're going to state it even more formally. Dense sets contain 3-term progressions. More formally, you fix a density delta, and then it's true that any subset of your interval, which has density at least delta in that interval, contains a 3-term progression with non-zero common difference, i.e. it's not the trivial 3-term progression x, x, x. Okay. Or the second possibility is, once you fixed your density, the length of the interval was small in terms of that density. So perhaps I can ask a question. Can people see my annotations on the slides? Oop. Doesn't look to me like they're coming through.
No.
You can't see my annotations. Oh, you missed some gold there. You really didn't miss anything. Let me see if I can. That's coming through okay. Great. Okay, I apologize for that. Let's soldier on. Okay. Okay, so just to rephrase Roth's theorem, either we get 3-term progression or our interval was small. Now, last time we talked about solving equations in sets of integers, and we did that via Fourier analysis. How do you encode a 3-term progression as a solution to a linear equation? Well, this triple, x, y, z, it corresponds to a 3-term progression if and only if we solve this equation x minus 2y plus z is equal to 0. So you can parameterize solutions to this equation as 3-term progressions. And now we're in business because now we've got Fourier analysis on our side. Okay. And we've already done a lot of the work in proving Roth's theorem because we showed last time that if your set is Fourier uniform, we'll revise what that means in a second, then it contains lots of solutions to a linear equation. So we take a set of integers and we assume it's got density delta and that it's epsilon Fourier uniform. And what I mean by that is when you look at its Fourier transform and you compare it to the rescaled Fourier transform of the interval, and you're rescaling by the density of your set, then that's an epsilon fraction of its maximum possible size, which is the trivial coefficient, Fourier coefficient of your set. So in some sense, the Fourier transform of your set behaves like a rescaled Fourier transform of the interval. So if both of those assumptions are true, then we've got this naive heuristic, this asymptotic formula for the number of solutions to our equation in our dense set. And it's equal to the number of solutions in the interval. That's given by this formula here. The number of solutions in the interval scaled by this cube of the density, because we're working with a 3-variable equation, plus an error term. And the error term is depends on the level of Fourier uniformity. So the more Fourier uniform you are, the smaller the error term. And it's epsilon times n squared. And just to say, this number here is about n squared, the number of 3-term progressions in the interval. I think it's actually more like half n squared. But up to absolute constants, it's the right order of magnitude. Okay, so we solved Roth's theorem. We've actually obtained an asymptotic for the number of 3-term progressions in a dense set. But the problem is, not all sets are dense. Not all sets are dense. What am I on about? Sorry, I'm reading chat and thinking at the same time. Not all sets are Fourier uniform. What is true is that almost all sets are Fourier uniform. A random set is Fourier uniform. But lots of interesting sets aren't Fourier uniform. Last time we met these examples of Bohr translates. For instance, a congruence class, mod 10, or a short interval. These are both structured, they're not Fourier uniform. This asymptotic formula doesn't hold. And we met some more general examples of sort of Bohr sets coming from irrational frequencies. Okay, so lots of interesting sets, lots of interesting dense sets aren't Fourier uniform, so this lemma is useless. So let's try and find a little bit of Fourier uniformity. So we're in the situation where we've got an arbitrary subset of our interval, and this local Fourier uniformity lemma, which is going to be key to how we prove Roth's theorem, is we take our set of integers in the interval, we turn a crank, and out spits this progression P, which has some nice properties. Our set A is as dense on the progression as it is on the global interval. So this notation here, I'm just using for the density of my set A on the progression. Okay, so I'm as dense, I've not lost density by passing to the progression. And the second conclusion is I'm Fourier uniform on the progression. If I compare the indicator function of the set intersected with the progression, that's here, that's comparable to this rescaled Fourier transform of the indicator function of the progression. And we've rescaled by the density of our set in the progression. Now, the keen-eyed amongst you will notice this isn't actually the definition of Fourier uniformity on a set that I've, for instance, written in the notes. This is actually a weaker notion of Fourier uniformity. And the difference is, if you wanted to define Fourier uniformity as I have in the notes, it would be this expression is at most an epsilon fraction of the Fourier transform of A intersect P. Okay? So there's a difference between these two statements. One says you're an epsilon fraction, and just to say, with my normalizations of Fourier transforms, this expression is the cardinality of the set P, and this expression is the cardinality of the intersection. So this is a weaker notion of Fourier uniformity, but it's sufficient for our purposes. But one thing you should note is that if I'm sparse on my progression, then actually this weaker notion of Fourier uniformity has no content, because all sparse sets satisfy this inequality. Simply because for a sparse set, both this quantity and this quantity are little o of the length of the progression. So although this local Fourier uniformity lemma seems to apply for all sets of integers, actually really only has content for dense sets of integers. Okay, so we've got some weak Fourier uniformity, which is only useful for dense sets. And the last conclusion, I've sort of compacted down into some nice notation, and it's completely, it's not transparent what that means at all. What I'm asserting here is that the length of my progression tends to infinity as the interval length tends to infinity, provided my uniformity parameter is fixed. Okay, and I've just compacted it down to some very unintelligible notation. So the notation says n is bounded in terms, the length of the original interval is bounded in terms of this level of uniformity we're seeking, and the length of the progression spat out by this lemma. But the progression can be made as large as we want, as long as we want. So there are the three conclusions. We've not lost density, we're Fourier uniform, and the progression can be made as large as we want, if we're willing to make our original interval as long as we want. Okay, so a way to think about this is, here's a set which I generated by constructing a random subset of the congruence class 10 mod, or 10 mod, what am I saying? 0 mod 10. So I generated a random subset of 0 mod 10 of half the elements of that congruence class. And I also generated a random subset of this subinterval between 100 and 120. So two randomly generated sets, and I took their union. This set's not going to be Fourier uniform. It's got a very large Fourier transform at the frequency 1/10. But if I focus down on either the 0 congruence class, mod 10, or I focus down on this subinterval, I'm going to obtain a random set. So the local Fourier uniformity lemma, if you turn the handle for this particular set, it would either output you the congruence class as your progression or the interval. And on either of those choices, you've got Fourier uniformity. So if you're happy to localize, you can get Fourier uniformity. Now, we showed that sets which are Fourier uniform satisfy the naive heuristic. We can asymptotically count solutions to an equation. The same is true for this local notion of Fourier uniformity. This weaker notion of Fourier uniformity that we met was guaranteed by this local Fourier uniformity lemma. So let's state that as a lemma. If you've got a subset of a progression, actually, this lemma doesn't need P to be progression at all. It can be an arbitrary set. And your set A has density delta on the ambient set P. And you've got this weak notion of Fourier uniformity. These Fourier transforms are comparable after rescaling the Fourier transform of the ambient set. And they're within an epsilon fraction of this rather crude bound. This latter thing is the size of my set, of my ambient set. So you're an epsilon proportion of that. And then you can obtain this asymptotic formula. The number of 3-term progressions in your set is the density cubed times the number of 3-term progressions in the ambient set, plus an error term, which is epsilon times the square of the cardinality of the ambient set. So this is completely analogous to what we wrote before, and the proof works. Even though our previous lemma of this form assumed the stronger notion of uniformity, actually we didn't use that stronger notion of Fourier uniformity in the proof. The weakened Fourier uniformity suffices. Okay. So this is good news, because it looks like we can pass to this subprogression guaranteed by the local Fourier uniformity lemma, and we'll generate lots of 3-term progressions there. Well, what this is really, is there a question? Okay. Perhaps not a question. We've reduced this combinatorial problem, counting solutions to our equation in a dense set. We've reduced it to a number theory problem, and that's counting this main term here. Counting 3-term progressions in this ambient set P. And we need to show this is definitely a main term, so it's of order of magnitude P squared. So let's solve the number theory problem. And I wouldn't class myself as an official number theorist. So this is an easy number problem, one that even I can solve. Okay, what does a progression look like? It's a translate. You take an interval, 1 up to m, you dilate it by q, and then you translate by a. And because the coefficients in our equation, x minus 2y plus z equal to 0, because those coefficients sum to 0, and the equation is homogeneous, you can dilate and translate the variables in that equation, provided you're dilating each variable and translating each variable by the same amount. You can translate and dilate, and you don't affect whether this equation is soluble or not. So we're working in the integers here, just to respond to a question in the comments. Okay, so our equation is translation, dilation, invariant. And the upshot of that is if you're counting solutions, counting three-term progressions in your set P, it's the same as counting progressions in the interval 1 up to m. So I've taken one number theory problem and reduced it to an even easier number theory problem. How do you count solutions in this interval? Well, if you fix x and z, elements of this interval 1 up to m, then y, solving this equation, is equal to the average of x and z. So if x and z are in the interval, how do you guarantee that y, the average, is also in the interval? Well, you just need x and z to have the same parity. So how many pairs are there in this interval which have the same parity? Well, there's the number of odd numbers in the interval, squared, and the number of even numbers in the interval, squared. And you can bound that easily using Cauchy-Schwarz and get this lower bound of half m squared, and the upper bound is up to lower order terms, it's exactly the same, half m squared. Okay, so the progression has lots of three-term progressions. This is probably not surprising to most of you. So now let's prove Roth's theorem using this local Fourier uniformity lemma, plus a little bit of number theory where we counted progressions within a subprogression. So we take a set A in our interval, 1 up to n. It's got density delta. Turn the handle of our local Fourier uniformity lemma, and we output a progression P, where the length of our original interval is bounded in terms of the level of uniformity we're looking for and the length of the output progression P. The density of our set A on the progression P is at least the density on the original interval. And we've got this local Fourier uniformity, some weak version of Fourier uniformity. These transforms are comparable up to an epsilon factor. So that's just the Fourier uniformity lemma. Now we use the fact that with this notion of local Fourier uniformity, we've got an asymptotic formula for the number of solutions in our set intersected with this progression. It's equal to the number of solutions to our equation in the progression times the density of our set on the progression cubed. Well, that's at least delta cubed, because the density of our set on the progression is at least delta. And we've got this error term, epsilon times p squared. We've calculated this main term. It's the length of the progression squared times a factor of a half. So we've got a nice lower bound now, and you can see if you take epsilon sufficiently small in terms of delta, you're going to obtain a nice lower bound for the number of progressions in your set A constrained to this subprogression P. So you take epsilon to be, say, cubic, or something smaller than cubic in delta. This 100 here is completely arbitrary, and I've made it up. 100 depends on the implicit constants in this big O term. Maybe you need to take 1 over 1 million, I don't know. Just to fix ideas, imagine we can take delta cubed over 100, and then we get this lower bound. The number of three-term progressions is up to implicit constants, delta cubed times the length of the progression squared. So the progression, just to answer your question in the chat, the progression P is an arithmetic progression. It's not an arithmetic progression mod P. I haven't mentioned any cyclic groups mod P in this lecture. Nothing is going to take place in cyclic groups. Okay, so we're done. We've generated a ton of three-term progressions in our set A. Or have we? The problem is, you can generate quite a lot of three-term progressions for very uninteresting reasons. For instance, x, x, x solves the equation. So that's a trivial three-term progression. And maybe this lower bound we've got is just generated by counting all these trivial progressions. Well, imagine that if A had no 3-term progressions, then the only 3-term progressions it contains are these trivial ones. So in that case, we can really crudely bound this count here by the cardinality of A intersect P, because that's the number of these trivial 3-term progressions there are in my set. So if A doesn't contain any 3-term progressions, then this intersection doesn't contain any 3-term progressions. So the only solutions to the equation picked up by this count here are those diagonal solutions. So no 3-term progressions gives you this upper bound, very crudely. Okay, so if that's true, then the length of P, if you just sort of compare the upper bound and the lower bound, the length of P has to be bounded in terms of the density delta. Okay, so this assumption of no 3-term progressions guarantees that the length of this progression is bounded in terms of the density. But the length of our original interval is bounded in terms of the level of uniformity, which we took to be some power of delta, and the length of the progression, which we know is also bounded in terms of delta. So we've deduced that no 3-term progressions implies that the length of our original interval is bounded in terms of delta. And that was the second possibility in our statement of Roth's theorem. Either we get 3-term progressions, or the length of our interval is bounded in terms of the density of the set we're working with. Okay, so just to summarize, this local Fourier uniformity lemma gives us Roth's theorem. And the same argument works for any linear equation in 3 or more variables where the coefficients sum to 0 and there's no constant term. So you can characterize, or you can prove that this class of equations always has a solution, a non-trivial solution in a dense set of integers. And it's quite easy to show the converse to that, that if your equation doesn't have coefficients which sum to 0, then you can find a dense set which lacks solutions. So that's a nice exercise if you want to sort of familiarize yourself with these methods. But we've reduced our task in proving Roth's theorem to proving this local Fourier uniformity lemma. How do we do that? We're going to prove it by this method of density increment. So the key ingredient for the density increment method is a density increment lemma. What does that look like? So we take a progression and we take a subset of integers which doesn't have the Fourier uniformity we want. So we're trying to find this subprogression where the opposite of this inequality holds. This is the negation of this weak notion of Fourier uniformity. Given those two assumptions, there exists a new progression, P prime, whose length is about square root of the previous progression, and where your set is substantially denser. Its density increments by an amount which is just some small constant which depends on the level of Fourier uniformity you're seeking, epsilon. That's this number. So this is the density increment. We've incremented the density of our set A by passing to this subprogression. So the local Fourier uniformity lemma is just this density increment lemma iterated many times. How does that go? You initialize your iteration process with the full interval. That's your first progression. And you ask whether you've got the Fourier uniformity you're looking for. This is the Fourier uniformity we're striving for. If it is, the process terminates, we've obtained our Fourier uniformity lemma, local Fourier uniformity. So we can assume that's not true. And if it's not true, we're in this situation. So we can apply the density increment lemma. We obtain a new progression whose length is square root of the first progression and whose where the density of A on this set has incremented by some constant depending on the level of uniformity epsilon. So that was just iterating once. Now let's iterate again and again and again. We end up with n progressions. And we ask ourselves the question, do we have the local Fourier uniformity we're looking for? That's this assertion. And if we do, we're done. We've got our local Fourier uniformity lemma. If not, we apply the density increment lemma, and we get a new progression, p sub n, whose length is square root of the previous progression, and whose the density of our set A on this new progression, there's a typo here, this should be Pn minus 1. The density of our set on this new progression is at least the density on the previous progression plus this constant amount that we're incrementing every time. So if we apply these bounds recursively, we deduce that the length of our progression is some power of the interval we started with, which had length n. And the power is some function of the number of iterations. And there's this implicit constant here depending on epsilon. And the most important thing is this. The density of our set A on this progression P, Pn, is growing linearly with the number of iterations. So why that's important is a density is bounded by 1. So this can't continue to grow. It has to terminate at a number of iterations, which is some function of epsilon, because there's some implicit constant here depending on epsilon. And if n is bigger than 1 over that implicit constant, then we've got a density exceeding 1. So this procedure definitely terminates at some point, yielding this local Fourier uniformity and thereby giving us the local Fourier uniformity lemma. Okay, so we've reduced Roth to proving this density increment lemma. How do we do that? So the density increment lemma, let's just look at it again. It takes a progression where you don't have local uniformity, and it spits out a new progression whose length is bounded in terms of the previous progression, and you've got this density increment. Let me just fix our progression P to be the original interval 1 up to n. So, and this is sort of an informal sketch of what the lemma is saying. You have this non-uniformity assumption. When you compare Fourier transforms with the rescaled transform of the interval, you're exceeding the length of the interval by some epsilon proportion. And you want to conclude that you can find a progression where you've incremented the density. So delta here is the density of our set on the original interval. And we're assuming A is a subset of the interval. It just simplifies things to work with this progression as opposed to some arbitrary progression P. So let me give a sketchy proof of how this goes. Let's define the balanced function of our set. So we take the indicator function of our set and we subtract the indicator function of the interval rescaled by the density delta. So this is balanced because its sum is 0. Because when you sum the indicator function of the set, you get delta times n. When you sum this thing, you also get delta times n, and those things cancel. So we're assuming that there is some frequency alpha such that the Fourier transform of the balanced function is at least epsilon n in magnitude. That's just this here. It's the same thing. The Fourier transform is linear, so that's why this is our assumption. Okay. Now we don't want to, what we want to conclude is that there is some progression where the sum of our function, our balance function, over this progression is at least epsilon times n, the length of the progression. So why is that? So let's look at this. Assuming that P is contained in our set N, this sum here, it's a sum over x in P, indicator function of our set, minus delta times sum of x in P 1 over 1 of n of x. Okay. So this term is A intersect P. And this term, if P is a subset of our interval, this is delta times the cardinality of P. So if this is greater than epsilon P, when you divide through this expression by the cardinality of P, you obtain this density increment up here. Okay, so we have to worry about some sort of whether progressions are contained in our interval or not, some kind of boundary issues, but let's sort of put that under the carpet for now. I just want to communicate the ideas behind this proof. Most of the technicalities come about because you're worrying about boundary effects between intervals. So we're assuming this, we want to prove this, and the idea is you partition the interval into these progressions where the linear phase E alpha x is approximately constant. It's not clear that one can do that. I'll show on the next slide that one can do that. But imagine that you could do that. Then here's our non-uniformity. This number is at most this number. Let's, instead of summing over all integers, let's partition this sum into these individual progressions, P. So I've just rewritten the sum, so now we're summing over all the possible progressions and then summing over x in each progression. And here, before we had the number capital N, and you can rewrite n as summing over all progressions, cardinality of the progression. Okay. Now we're assuming E alpha of x is approximately constant on these progressions. So this is approximately sum over P, sum over x in P, f of x. And you could just pick your favorite element of the interval, x sub P. Okay? Because this phase doesn't vary much along the progression, you may as well replace this arbitrary x in the progression with some fixed element x sub P in the progression. It's approximately equal. And then you could take this phase out here. So let's do that. This is where I try and get fancy with okay. So we've taken it to the outside. Now we crash through with the triangle inequality with absolute values. And that removes the phase, and we're just left with a sum over P. This is what we get. We can bound this epsilon times this sum over P, that's here, with we're summing over P, all these individual progressions, absolute values around the sum of F along each progression. But the point is I've removed the phase from this sum. So this is looking good. We're wanting to show this, remember? And now we could apply the pigeonhole principle and we would have established this fact, but there's this problem about absolute values. How do we get rid of absolute values? Well, let's remember that the sum of our function is 0 because it's balanced. It's a balanced function. So we can add it to either side of this equation with this inequality. We don't affect the inequality. This number is 0. But this picks up when the absolute value is, the thing inside the absolute value is positive or negative. So when this sum here is positive, you collect 2 times the sum, because the sum is equal to its absolute value in that case. When this sum here is negative, it cancels with this, and you get 0. So we've removed absolute values. Okay. So now we're in the position where we can apply the pigeonhole principle. We know for some p, this sum, sorry, what am I on about? Some p, and this sum here is at least epsilon times the length of the corresponding progression. Because if all these things were smaller than epsilon times the length of the progression, then this inequality wouldn't hold. So that gives us our density increment. So if you're willing to buy that, and if you're not willing to buy it, I encourage you to go and read the notes for the course. If you are willing to buy it, let's try and wave my hands and convince you why you can partition the interval 1 up to n into subprogressions where this linear phase is approximately constant. So let's first think about how these phases behave. These phases are what appear in our Fourier transform. That's here. Okay. If you want to compare if you want the phases to be approximately constant, you have to compare how close they are to each other. These are points on the unit circle. Let me draw the x-axis. And if you want to compare the distance between these two phases, then it's comparable. The distance between the 2 points on the unit circle is definitely bounded by the arc length between them. And up to absolute constants, that's bounded by the difference in angles. So this maybe is θ1, this is θ2. So that's what this is saying here. Comparing phases, you can just, there are sort of, it's enough to compare the difference between the angles they make. Okay. This is a metric here. So we can apply the triangle inequality because this is an integer, x minus y. So repeatedly applying the triangle inequality, and you can bound this by the integer, or the magnitude of the integer, times the frequency times this common difference q, where q is coming from a progression, the common difference of this progression p. So maybe I should say I'm thinking of p as a plus q dilating m. Okay, I don't know why I've spent so much time on this inequality. It's just calculus. So what we're going to do is we're going to choose some common difference q, which makes this as small as possible, this fractional part. And you can do that using Dirichlet's theorem on Diophantine approximation. If you're not familiar with that, it's essentially the Bohr set lower bound that we proved last time, or proved in the notes anyway. Okay, so you can choose a small common difference q, which gives you a small fractional part. And then if this is our progression, a plus q dilating the interval 1 up to m, then the difference between two element, what am I saying? Stare at this long enough, and provided the length of your progression isn't too long, the phases are approximately constant on the progression using this inequality. Okay. Now, there's a balancing act to be performed here. You need to choose the common difference q to be small, because that allows you to make the length of the progression quite large. But you need to choose the common difference q to be large to make this fractional part small. So there's a tension between the size of the common difference and the length of the progression m. And the optimal choice when you work out the details is to take m and q around square root of the length of the interval. And that's why in this density increment lemma, when we increment, we get a new progression, which is square root of the length of the previous progression. Okay, there's lots of details swept under the carpet there. Go and look at the notes. So I'm claiming that completes my sketch proof of this density increment lemma, which gives the local Fourier uniformity lemma, which then gives Roth's theorem. But I just want to observe that what we did was we counted solutions to our equation locally on some subprogression using density increment. And there are many applications where you want to globally count solutions to your equation in a dense set. How on earth do you do that? Because globally, your set might not be Fourier uniform. So our solution to this is going to be this technique called arithmetic regularity. And we essentially decompose the interval into a bounded number of pieces, which are algebraically structured. They'll look in some sense like Bohr sets, or translates of Bohr sets, or smoothed out Bohr sets, sort of weighted functional versions of the indicator function of a Bohr set. And on each of these pieces, we'll get Fourier uniformity. Now, if you want, you could just think of these as dense progressions. They're not in general dense progressions, but that might be easier for you, just to get a picture of what's going on in your head. So here's a picture. How did I generate this set? I took some random subsets of these intervals of length 20, and then I threw in some extra random points. Okay, so arithmetic regularity in this case would output a decomposition into intervals of length 20 and these would be the Bohr translates. And on each of these structured pieces, I'm either random or almost empty, which is another way of being coarsely or weakly Fourier uniform if you're very sparse. So we'll see that on each of these pieces, our set is Fourier uniform on almost all of these pieces. And then essentially using the same Fourier uniformity argument we've used again and again, you can actually count solutions between these pieces, because on each of these pieces, you've got Fourier uniform sets. So you can count solutions between pieces, and you get the usual asymptotic, a product of densities times the number of solutions in the ambient fibers. Okay. And then there's the number theory problem. You have to show that the number of solutions within the ambient fiber is large. Or you have to actually count the tuples which contribute a large count. So in this case, if we add this interval to this interval, we're going to be in this interval, and we're not going to have any solutions. But we can generate lots of solutions by adding this interval to itself to get to this interval. So there's some kind of more coarse scale arithmetic problem you have to solve. But that's what we'll look at next time. Okay, so that's all I had to say. So now I'm going to stop recording.